Okay, so let's actually define the center of mass of some collection of massive objects. So let's say we have a collection of massive objects, and we take each mass and we multiply by its vector position in space. So this is, M1 R1 plus M2 R2 plus, from I to, say, N, dot, 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 M, N, Rn. And let's consider the derivative in time of this sum and that is just a sum from I equals, it's I equals 1 to n. So I equals 1 to n of m masses times velocities, because we have dr by dt and the mass is a constant. And now let's take another derivative. Let's take a second derivative in time of this quantity, I equals 1 to n of mi ri. That will give us a sum of masses times accelerations. But of course we know from F equals ma that that's the sum of all the forces acting on the individual objects. So that's the sum Fi. But let's look at the second derivative in time of the sum from I equals 1 to n of mi ri over the sum total of the masses. So this is, this applies to this because this is a constant. So we have that this is equal to the sum of the forces, of the n forces, over the sum of the masses, which is just the total mass. Let's just call it m, where the sum over all the masses is equal to the total mass n of the system. And now we can define our center of mass, RCM, the position of the center of mass, is the sum of masses times positions. So it's sort of a weighted sum over the total mass of the system. And basically what we have is that the second derivative of the center of mass of the system, which is the geometrical center if the mass is uniformly distributed, is equal to the sum 1 to n of the forces divided by the total mass. In other words, mass times the acceleration of the center of mass is equal to the sum of the forces. That's an abstract idea. We could write this as mass times acceleration center of mass equals to the total force, F total, if you will. Maybe that's a better expression. But basically what this is telling us is that we have some extended object, some extended two-dimensional object, and we don't have to worry about gravity pulling on each little part of this, right? All of these, where are we? All of these, we just have to place the net force mg. So if the mass of this object is m, there's a net force mg acting at the center of mass, and that's sort of, if the mass is uniformly distributed, that's kind of like the center of mass there. And this is crucial for figuring out how the force of gravity either rotates or doesn't rotate the object about some point or some axis.